Hello again, everybody. Welcome to today's webinar on troubleshooting your MASTA model. We've put this webinar together based on some common themes that we see through the customer support department here at SMT, and we thought they'd be valuable to share them. So today's agenda is so first of all, we're going to look at some tools in MASTA for troubleshooting your model. So should something go wrong, if your model fails, or if there's something that you can't do in MASTA, we'll have a look at the tools for that. Then we'll have a look at some example models, looking at things that we've seen in the customer support department that have commonly occurred, and show you how to go about fixing these and the tools that are available there. I'm going to do a section on convergence. Now, I'm not going to go into too much detail into the convergence. There's plenty of things that can happen here. So what I'm going to do is going to give an overview of how the model works and how the convergence comes into play in some common problems. And then I'm going to look into a hints and tips section where we're going to have some smaller problems and smaller fixes that we think it might be valuable for you to know here. Okay, so in MASTA there's a series of tools for troubleshooting. So the first one is the most obvious one that we should all know about, is the status bar. It's very important. It will tell you the first line of information that you will need. After that, we can have a look at the 3D view. It's not only just a nice graphical representation of the model, but it does also contain some very useful information for if your model was to fail. In each report, we also have the node positions, displacements, and forces tables. Now, these can also give you a valuable insight as to forces and displacements that may be unexpected in the model, being able to narrow the problem down to a certain area of your model. The Convergence tab and the highlighted components. This is a nice useful tool if your error message at the bottom of the screen is model has not converged. We can have a look into that in a little bit. The modal analysis tab in the FE section. Now this will give you some good clues as to whether your FE has been brought in well, whether there are any problems with the setup either in the preprocessor or in MASTA. The model constraints. This is a section in settings which what we have done here at SMT is give the best estimate as to what these model constraints should be. Some of them are set to standards, and then some of them, as I say, are estimates. Your company may have different constraints that they wish to have on the model. I'm not going to go into this in too much detail, but you can find this in the settings in MASTA. Load case overridable settings. Now, this seems a bit of a strange one, as this is a setting for each load case, but this will give you the opportunity to turn certain sections of the model off only on this load case, and you'll be able to use this for diagnostics. If your model doesn't run, you can, for instance, turn the FE off, or you can turn certain calculations off, which may be not allowing your model to run. We're going to have a look at the Parametric Study Tool and how to find out what the problem is with your parametric study and the different ways that you can get into the load cases that have failed. And also it's worth noting that if your problem in MASTA is in a mode, in an advanced analysis mode, then the problem may be lying further back down the line. It may be down to a power flow issue. It may be down to a system deflection problem. It could be any of those. So it's well worth double clicking on the status bar and going back to in the chain to find the analysis where the model has actually failed. So that's the list of tools that we're going to look at, and are a good list of tools to start troubleshooting your model in MASTA. And we can now move on to the next bit, where we're going to have a look at some example models and how some of these tools can be used. Now, the first example model is the Parametric Study Tool has failed. And we can have a look at the different options that there are available in MASTA to look at which run has failed and how to advance your search for the problem in the model. Okay, so in this model here, I have a basic single gear pair on 2 shafts. And if I was to run this in Parametric Study Tool, I've run 2 different studies. So the first one is a changing design study, where we've put the helix angle from something reasonable all the way to something very high. And we'll run the study on this. And we also have a load case settings one where we're not changing the design. Now, both of these will have slightly different outcomes at the end in terms of how to go about finding the problem in the model. So I'll run both of these now. And I'm sure you all guessed that there would be some failures in this. So first of all, I'm going to look at the load case settings. It's already popped up onto our screen the first stages into this. So we can see that in our load case settings, we have in the status bar an error down here. But when using the load case settings, and this, in case I wasn't particularly clear first time round, this is when you haven't got the change in design box ticked. When you run it and you have a failed run, the load case for that will appear here. So if I click on this, we can then go into the load case here, and we can see that on this failing load case, we have our maximum torque, which is very high and is why the model has failed. But we can now take this load case and we can go and run it in system deflection. And when we've done this, we can see that it's failed just as it did in the parametric study, but now we have much more information to have a look at it. So I'm not going to go into any more detail with this model right now. We can look at some of these options down here very soon. But the point that I was trying to put across with this is that you can access the load case and take it into system deflection mode, which was the analysis that we were running parametric study. And we can get more information out that way. If we were to go back into Parametric Study Tool and we were to select this load case here, which is changing the design, there's a slightly different process that we can follow. So we can see that we have 4 out of 30 analyses failed. Now what we would do is we would head to the Reports tab, where we can see all of our different variables. We can see our very high helix angles down here, and we can have a look at which runs failed. So this is on the root assembly. You can only find it on here. Now, we have the 4 runs at the bottom which have failed. And there is an option to either save this design. So what you can do is you can save the design at which our model is 61.3793, and that will be your new master model. Or we can open the design in a new tab. So I'm going to select the Open Design in New tab. So this is the Run 27. And once again, we can take it into system deflection mode. And on this load case, we can diagnose the problem from here. Like the first one, I'm not going to look into this too much further. This was just a basic look into how to find the problem in parametric study so that you can investigate further. Okay, so something else that comes up in customer support quite a bit is the meshing of the teeth providing a torque transfer problem. Now, I'll get this example just. Open it now. Okay, so I've based this on the same model again. So it's the single gear pair. It's the helical gear set example out of the examples menu, which has been slightly modified if you wanted to try this at any point. So what we've got is a shaft that's been replaced by FE. Now, we've changed the shaft profile so that the gear blank goes up towards the root diameter. It's not quite at the root diameter, but it's very close to it. And if I go to run this now, we get an error message that says the imported FE does not appear to be correctly transmitting torque. So with this problem here, we can check to make sure, just to be sure that this is the FE that is causing the problem in the model. And if we go into this option here, we can turn the FE off just for this one occasion, and we run it. MASTA's happy with that, it runs. So we know now that there's a problem with the FE. Okay, so this means I need to go to the imported FE tab and have a look at my FE model. I'm not going to go hunting around too much in this model right now. Finding this without knowing where to go to could take a while, but the problem that we've seen is solved, or the problem that we see is caused by this FE that's generated for the gear teeth doesn't have enough space to extend because of the gear blank mesh. So you see that the gear blank mesh is very close to the root diameter, and this now doesn't give an opportunity for the tooth mesh to be formed and also to be stitched with an MPC connection to the gear blank. So what we do for this is, and we recommend this for all shafts with gear teeth that are being applied to it, is that we just pull back the gear blank diameter a bit. Maybe go a little bit further than that. In terms of the system model, this will have no effect. It will still be the same stiffness. But what it will allow us to do now is to go back into the model setup tab, and we can remesh this. And we can see now that we have much more space down here, and we no longer have the high aspect ratio elements, which were causing us a bit of a problem, and we have a much nicer mesh. The other thing that is a bit of a clue is if the tolerance for zero frequencies has to be adjusted here from its default, which I've done to show you this, that's always a bit of a clue. The default is 0.01. You can change it if you want, if you think that that's unreasonable. And then it's telling us that we have 3 rigid body modes, where we should be having 6 for a shaft. And then if we go into the modal analysis tab, we do have a much nicer mesh, and our model frequencies are much lower than they were before. My apologies, I should have showed you that. But we were getting around about 0.16 in this 6th mode. And now we are getting slightly better frequencies, but they're still not perfect. If I was to put this at 0.2, this does run in system deflection mode. However, it's not completely solved. The problem is not. So if I move this back to the default setting, when we have these 2 surfaces here for the MPC connections, the calculations used do depend on which surface is the master surface and which surface is the slave surface in the connection. So if I turn the model transparent again, so you can see the one surface here and we can see the other surface here. MASTA will give you the option to swap these surfaces. And then we can take this back to the mass and stiffness tab, and the calculation can be performed again with more specific, with the master and slave surfaces specified better. Okay, so now we've run this. We can see in the status bar that our error for the wrong number of modes has disappeared. And we can take this back to system deflection mode. And now that this has been corrected, it should be run nicely. Okay, and that's this model. That's it for this model. Please don't hesitate to ask any questions. There's a box for you to type questions into, which if they're nice and short and simple, then I can give an answer to right away. If not, then they all get saved at the end, and we can answer each one individually. Okay, so that's these two done. Axial clearance bearings are another thing that come up quite a lot in customer support. They're a little bit, how would I describe it? They're quite small things in the model, but they can make a very big difference if they're not put in correctly. So they're designed, first I will show you the model. So they're designed to represent a contact between two components. So if I go into the 2D view here, we can see that we have two shafts, and the contact between them is being represented by an axial clearance bearing. This shaft here is grounded, and then we have by the rigid connector. And we also have a point load here, which is applying a push in one load case, so a positive Z, and the pull, which is a negative Z force. And we can run both of those. And we can see that in the push load case, we can see the deflections all moving. We should up this a bit. So this is as you see it in the 2D view. So it's pushing together, which is fine. If we then go to the other load case, we can see that just with a little bit of deflection, it's flying off into nowhere. So it's essential to get these the right way around. And it sounds very simple, but we've seen many models come in for diagnosing a problem, and it's just been one axial clearance bearing that's been causing all of the trouble. So it's well worth knowing. For instance, we have this this model here. So in the fifth gear, we have a failure. Now this is where I'd like to bring to your attention the highlighted components in the convergence. So if we double click on the error message, it will isolate the component which is causing the problem for that error message, and that brings us down to this area here. So what we have is a needle roller bearing on a gear blank. So the gear blank isn't converging because there's too much axial displacement in it, and these are not converging either. If we go to the 3D view, we can see there's lots of displacement coming over here. We need to the final iteration. There we go. And we can see how far away this this component has moved. So that's one of the good things about the 3D view. If something's moving that you don't expect it to, then it's a very easy to see thing. So what we have here is the axial clearance bearing. As there's no axial support in the needle roller bearing, we can go into the move component or the connect component tool. And there's a function here just to swap the inner with the outer, so you don't need to go connecting it all over again. And you can see now that we've swapped it, it's happy with that, and we don't have anything flying away. Okay, so I have one more example model to show you before we move on to the next section, where I'm going to have a brief overview of the model running in MASTA and a bit of the convergence and how that would work. So this one here is how to look into your FE connections and the modal analysis tab. I have a model here. So this one is based on the simple housing example that we have in MASTA. Okay, and I'm sure you guessed it's not going to run. So in this case here, as we did before, we can isolate the housing and we can override it. And we know that that's going to run now without the housing. So we know that the housing is definitely the problem here. Now, in imported FE mode, we also have a 3D view. So we have all of these options along the top, which can help you identify different parts of your FE. Now, what it was saying in the error message before in system deflection mode, if we run this again with the housing on, is that we have no rigid body modes. So this is the opposite to the first FE example that we did, where we had more rigid body modes than less rigid body modes than we wanted. Now we have more rigid body modes than we wanted. So if we go into here, we can have a look at our modal analysis. So if we were to look at this, and we can run the first mode. So this is one of our rigid body modes. And if we press this, we can see that when the mode is being played out in the visual guide, that there is no constraining it. Just for comparison, we have the original housing here, and we can see that that's constrained here. Go back to this one here. This is the one that we're currently interested in. So we can take this into the model setup window, and we can have a look. So what the model needs is it needs some grounding points. So I've clicked to highlight the grounded nodes button, and as you can see, there's nothing happening here. What we would be expecting is to see some red highlighted zones, as we have with the running model. So this is what you would expect to see. And this would happen the same with the rigid elements button. So if you've got two sections of housing joined together, between those two sections, you'll see some of these this red highlighting. Okay, but we don't. Now this leaves us with a couple of options. So previously in MASTA, we would have had to take this back to our FE solver, check that we were using the supported commands. So in the MASTA help here, you can search for supported commands, and it will show the Abacus, ANSYS, and NASTRAN supported commands, which can be used in the FE files. We can check to see whether we're using the correct ones in there. Or if you're using later versions of MASTA, we've now added it so that you can ground your component in a couple of different ways in MASTA. So in here, we have the option to select different components or nodes or elements. So we can do individual nodes, we can do regions of nodes, we can do a surface of elements, or we can just do an element face. Now, the most basic way to do what we're looking for here is we can select a surface. So now we've got the selected surface, we can go to the Element Faces tab, and we have the option to ground the faces. So you can see now, if I deselect that, we now have a grounded face. We also have the option, if you're using a spring mount for your housing, we can also select some element faces at the location. To which we can create a condensation node at this point. And then from this condensation node, we have the option to create a point load, a bearing, or a shaft hub connection. The shaft hub connection being the grounding point that we can use. Okay, I'm going to delete that. That's not the method that we're going to use now. But we can move on to running the reduction. So while the reduction is running, just important to let you know that if you are using the grounding using a shaft hub connection, you will see 6 rigid body modes, and then the housing will be grounded by the shaft hub connection. So that's a different scenario. But in this case, you should see 0 rigid body modes. So we can go back to the modal analysis tab here, where we have a grounded surface, and we can play this, and we're now getting the expected mode that we were looking for in the first place. And you see that none of the first 6 modes here are 0 frequency modes. So if we now go back to system deflection mode, this should be able to run. Okay, and that's it for the example models that we have. I'm going to move on to the next stage, which is the convergence section. Okay, as I was saying, I'm not going to go into masses of detail regarding the convergence. It's a big topic. It can provoke a whole range of problems in the model. So what I wanted to do was to explain how the MASTA system model works, and how the convergence settings and how there can be problems with convergence with certain components. So as we were looking at this 5-speed transaxle model before, we can see that we have this node model in MASTA. So MASTA has generated all of these different nodes with different stiffnesses at all of the different components, and anytime something interesting happens with the model, so shaft dimension changes, and then it turns this into a simplified FE model, where what we do is we take the forces and displacement and run the MASTA calculations. So we will apply the forces to the torque and the boundary conditions at the grounding point, and then MASTA will calculate the displacement. Within MASTA, we have nonlinear calculations for gear meshes and bearings. So what it will do is it will have to perform different iterations in order to be able to calculate the correct displacement at these points. And what can arise from this is, particularly in this setting here where we have 5 different speeds, it has to know which of the gears is loaded. So it sets a tolerance, and all of the gears that aren't active should be below the tolerance for the power for the gear mesh to be loaded. In certain cases, what we can see is that particularly when using efficiency and you're seeing losses and drag in the bearing, and also for dual clutch transmissions which have an unloaded shaft in there. We can see that at times we are getting gear mesh and bearing powers which are over the limit of what it's considering for convergence. So if I go back into design mode, into the root assembly, we can go down to the Convergence tab here, where we have a variety of settings. Now I'd like to focus today on the power for a gear mesh to be loaded, and also the minimum force for a bearing to be considered loaded. So these are the two biggest things that we see. So if, for instance, your bearing has got 0.002 kilonewtons of force on, what could be happening within the model is there could be lots of displacement within the bearing. It might not actually be taking up the preload, and you may be considering this as an unloaded bearing. Now, in this case, MASTA will see it as a loaded bearing because it's over the threshold, but actually it's behaving like an unloaded bearing. So what you'd need to do then is consider what your own company limits are and what the what the policy is on what you consider to be loaded. Another thing that can happen is during the iterations, it can go between just below and just above for these convergence tolerances. So in which case, MASTA won't be able to decide whether it's loaded or not. So what is I'm essentially saying here is that to look into your model if it's not converging to see what's going on. Now to do this, in system deflection, we have a convergence tab. Now if I can go back to swapping the inner and the outer, we have it failed. We have a convergence tab at the top where we can look at any of the components in the model and we can see what the convergence behavior is. So for instance, we can see the left thrust pad did not converge. It's got a large axial displacement. And there we have it. We can see the chart of this. We can have a look at whether it's considered loaded in MASTA. We can have a look at the force on the inner race. In this case, that's definitely over the threshold. But if this was bobbing around the point at which the convergence settings were, then we can go and edit those. Obviously, I wouldn't recommend going and editing them if there is a serious problem in the model. If you're having to change these settings so that they are much different, then you're going to have to that's probably a sign that there is a bigger underlying problem in the model than just this happening. So that's a brief overview of the convergence in MASTA and how that works. Hopefully, if you're seeing any convergence problems, then you can use that information to go and have a look at what's happening in the convergence tab and compare that to what you're seeing in your convergence settings. So the last thing to look at in this webinar is some quick hints and tips. So these are things that we see commonly in customer support that maybe aren't quite big enough to build a model about, but they're definitely worth knowing. So the first thing I've already mentioned briefly that efficiency will have an effect on the system model in terms of drag, and it will change the torque that's going through the system. So it's not just a calculation that's being performed here, it's a whole new addition to the analysis. And sometimes this can tip models just over the edge to non-convergence or failure. So we can definitely look back using some of the tools that we've had to see how the efficiency is affecting the model. Like say in low torque and dual clutch transmissions, you might have to have a look at the default settings. Gears not rateable is another one that we see. Now, this isn't a problem at system level. However, it's probably a problem if you're looking to try and get your gear ratings out of it. So what this is caused by is if you look at the 5 nodes which are across the gear mesh, MASTA will calculate the forces on all of them. And if the force is in opposite directions on those, it knows that the mesh is loaded on both flanks. Now the rest of the system model will be it will be good, and it'll tell you exactly what's happening in the model. But as it's outside the scope of ISO 6336, MASTA doesn't do the rating calculation for it, as that would be not relevant. Being unable to fully specify a gear is another thing that comes up. So by default, I'm going to go back into MASTA now. If I take this, adding a gear into MASTA, and we go to a cylindrical gear pair, it's only asked us for this much information. And with this information, it can use the a DIN gear fit system to generate a reasonable gear set just from this basic information for when you're designing a concept gearbox. But the downside to that is when it comes to actually fully specifying your gear, as I'm going to find an example now in this one here, we can go to gear macrogeometry mode, select our gear. That's microgeometry mode. There we go, macrogeometry mode. We can go to the editor and we can select our gear set. If I go to the 2 thicknesses and the extended 2 thickness editor and say, I want to calculate the 2 thicknesses using the profile shift, but all of this is calculated. Now this very first setting here, all we need to do is turn that to none, and then that will give us some freedom. And then we just need to go through unchecking these boxes here and then just checking the ones that we want. Alternatively, if we start going around in circles and we end up finding something that's calculated that we don't want to calculate, we want to specify this, we can just start from scratch again. If we go up to the top here in the editor, we can go to the All Properties report. Now in here, there's a button which will select clear all 2 thickness specifications, and we can do that. And then when we go back to the editor again, we can see that everything has been cleared, ready for you to start on a blank sheet. And the last thing that I wanted to mention during this webinar is when you have multiple output power loads. So in this case, we could be looking at differentials. We could be looking at multiple output power loads for a variety of reasons. But if it's not working, then it's always advisable to go into the load case and specify the power split that you're looking for. So MASTA is deliberately slightly under constrained for this, which will give you the freedom to select more torque going through one of the half shafts of the diff, for example. But if you have 2 sides of the diff or 2 output power loads that have got 2 very different paths of power, you could see some power errors going on here. And going to the load case, as I show you now, we can take this example here. This one currently works with only the input speed and torque specified, but as I say, if it's got 2 different paths of power going through to the different outputs, then you may see a problem here. And then what we can do is just specify this one power output. And in this case, I want it to be approximately 50%, so we can do minus 25.5. And then we can run that and it will calculate nicely. Okay, so that is that's a roundup of everything that we thought that it would be beneficial to mention in this webinar to show you about troubleshooting MASTA models and the things that we've seen and how we troubleshoot them. If you have any questions, we are going to leave this open just for a few minutes. If they're simple questions, then I'm sure that we'll have time to answer them now. And if not, then like I say, they get saved to this this webinar for us, and we can contact you back with the answers to those. And if you have any queries that haven't been answered during this session, then please let us know at support@smartmt.com, and we will do our best to help you out as quickly as possible. And thank you for joining today, and have a good rest of the day.